Dear colleagues, I would like to present you the lecture about some controversial issues of large-scale bedrock landslides identification. Here is the plan of the lecture. First, I will introduce the problem, make a short overview. Then I will describe general principles of rock avalanche identification. We'll talk about discrimination of rock avalanches and moraines, the same rock avalanches and rock glaciers. I will talk about the abnormally large fan-shaped deposits and their origin, and at the end we will discuss a little how to distinguish seismically and non-seismically triggered rock slides. Let's start from the introduction. Large-scale bedrock landslides, especially those that cause rivers damming, belong to the most hazardous natural phenomena in mountainous regions. Correct identification of such prehistoric features and of their triggers is an important stage not only of the landslide, but also of seismic hazard assessment. It is especially critical in formerly or presently glaciated mountain valleys, where such bodies could be misinterpreted as moraines. If these bodies were really formed by glacial processes, what it means? First, they indicate recurrent late Quaternary glacial advances and retreats, reflecting the differently directed climate change during this period. Second, considering present-day deglaciation typical of most of the mountainous regions of the world, we can expect quite low probability of new river damming events in the near future, and correspondingly, landslide and associated outburst flood hazard and related risks are low unless the inverse climate change will occur. If, however, rock slide origin of these features is true, then, first, no significant glacial advances occurred during the time when these accumulations were formed, otherwise the latter would not survive. Second, there are no general restrictions of large-scale slope failures and river damming at any time at present, and thus landslide and outburst flood hazards and risks are much higher. Moreover, since rock slides, unlike moraines, could be triggered by strong earthquakes, the seismic hazard and risk of the study area could be high as well. Therefore, the correctness of our interpretation of such features predetermines not only further research activities, but also, at a large extent, the disaster mitigation strategy. Let's talk about general principles of rock slides and rock avalanches identification. I must say that there is a fundamental difference between rock slides and rock avalanches and other phenomena that form large debris accumulations at the feet of high slopes, like glaciation or deglaciation, rock glaciers, debris flows. While rock slides and rock avalanches can be characterized, at least in most of cases, as dry granular flows, the alternative phenomena could not take place without the intermediate agent, water in the liquid or in the frozen state. In many cases, rock slides and rock avalanches can be identified based on combination of debris accumulation in the valley, we can see it here, and of the concave headscarp above it, which volume corresponds well to the deposit's volume. It is the example of the Ayköl rock slide in Kyrgyzstan. Another example. A 2.5 kilometer long run-out rock avalanche about 55 kilometers west of the Toksum town, Xinjiang, China. Here we have its headscarp and well-defined elongated body. However, quite often it looks as if the deposit is much larger than the source zone, which pre-slide relief can be just assumed. Here is a good example. It is the Aydinullah rock slide, also in Chinese Tian Shan, very large feature, about 400 million cubic meter in volume. Here we can see its headscarp. It looks much smaller than the entire body. Most likely, the entire rocky spur had collapsed here. Besides, we can see that it bulldozed quaternary deposits that form now outer zone of this rock slide body. It can be seen here with quite distinct boundary between this outer zone and main part. Here we can see two of the set of variants of the Aydinullah rock slide reconstruction aimed to balance its headscarp and deposit's volume. Some older Pleistocene rock slides could not be identified just morphologically, since both their headscarps and the deposits have been reworked by erosion, at such extent that none of them could be identified univocally on the remote sensing images and even in the field just visually. However, careful analysis of the deposit's grain size composition and internal structure, as well as of their relationships with other geomorphic features, helps us to make sound conclusions on their origin. I will show you some examples. Here is the remnant of the Terek-Su rock slide body, quite large and quite old rock slide or rock avalanche. We can see its headscarp here on the mountain, and these hills on the other side of the river valley, on the rather high terrace, and arrow marked with B show the site where this photo was obtained. We see a coarse, blocky and well cemented carapace of huge limestone blocks, overlying heavily comminuted internal in lower part of rock slide body, which in turn rest on the alluvium, on the gravels. One more view of the same feature. We see here deeply eroded headscarp and this fan-shaped body with badland features on it, dissected by this river, is the remnant of the rock slide which remain on the source side of this valley. And origin of this material could be derived from careful analysis of the material on the other side of the valley. One of the best examples of rock slide that originated on the slope composed of different types of rock is here. It is the Pleistocene Kokomeran rock slide in central Tian Shan, about 1.5 cubic kilometer in volume. We see its headscarp and we see its body, and we see that different types of rocks are presented in the headscarp zone. Here is the model how this rock slide emplacement took place. Units that originally rest on top of the headscarp zone, overrun and overlay units that originally